Just formally welcome everybody today to the Institution of Agricultural Engineers lunchtime lecture with Daniel Hefft, who's talking about in situ rheology measurements. Now, I'm going to leave Daniel to explain exactly what that means to you because it's way above my pay grade. But what I will tell you is that Daniel is a member of the institution, he's a chartered engineer, and he is a food engineer, and he is a fine example of a member of our professional community. He's founder of the Engineering for Food and Drinks Special Interest Group of the institution. He's a postgrad researcher at the University of Birmingham, and he's the founder, director, co-inventor, and chief technology officer of Rheality. He's been working for numerous years in the food industry and is experienced in large-scale manufacturing, management and process. So what I'm going to do now is I'm going to pass you over to Daniel. Can I ask, just out of courtesy, if you haven't been muted, Sarah will probably mute you anyway, and we'll let Daniel share his screen and crack on. Thank you for joining us, Daniel, and we look forward to hearing from you what you've got to say.
Well, thank you, Andy. You make me sound much better than I am. Okay, can everybody see my screen? Oh yeah, everybody's muted. Can anyone confirm that you can see my screen?
Yes, I can see it.
Perfect.
Loud and clear.
Okay, so first of all, thank you for letting me having the next half an hour of your life talking about in situ rheology. So what I plan to today, I give a very short context and background. I talk very shortly about the Rheality company, the science behind it and the technology, what we have done and what we have planned for the future. I give a very short one-slide summary and then we can jump into questions and answers. And I promise I'm not loading anything with equations or crazy stuff, unlike most academics. So we are moving in the area of manufacturing liquid products, and that can be anything from my background being a dairy product like a yogurt, or in the agricultural context, something like a slurry or sludge waters or something you want to spray in your fields. So there are four key components of successful manufacturing, and those are: we want to have a stable and well-defined final product. And we want to apply, obviously, good manufacturing practice, and we want to be compliant with all of our supply chain process control strategies that obviously ensure product consistency and build in redundancies and flexibility. And I think that applies to no matter what industry you're working in. So what are the challenges or opportunities when we manufacture those liquid products? So we wish to understand what the microstructure is of our final product, because if we understand the microstructure, we will eventually understand how this microstructure will then influence the macrostructure. We want to know how to control or monitor those fluids during processing, and how you can do that is to measure the rheology. And I'm going to explain in a very, very short sentence what is the concept behind rheology. It's a sub-branch of physics, and it purely describes the study of the deformation and flow. You might have heard often people talking about consistency or viscosity, but rheology goes way beyond this. And if you look to the right side, and this is a very simple, generic, even from Wikipedia taking a picture, we can see rheology is unlike viscosity or consistency measurements, which are single point measurements. It gives you a curve, and we can then have different models or mathematical ideas behind it to describe how these fluids behave. In the simplest case, a Newtonian fluid where the relationship between shear stress and shear rate is linear, but you might also have things like Bingham plastic, like toothpaste, which sits solid in your tube, and you need to bring in some energy to make it flow, basically. It is a key physical property to describe fluids and their flow behavior under time and temperature dependency. And that is another thing where it will be very important to have rheology, unlike a viscometer measurement or consistency meter measurement, because these measurements are affected by time and temperature. Rheology takes those factors into account. So, as I said, rheology is important for manufacturing environments, and I think for anyone, and there's a very famous quote I always like to say from Heraclitus: everything flows, and I would say in nearly every industrial application, at some point, something will flow. In modern manufacturing, we often produce large volumes, but rheology currently can't be assessed in situ, or there are only very limited ways how you can do that. Again, it is a very key parameter. It's very important to have our process monitoring and our productability. And as said, we have a lot of risk meters for inline measurement devices. So just about Rheality Limited a little bit. As said by Andy, I've been the founder, I have been the co-inventor of the technology, part of my postgraduate research at Birmingham, under supervision of the person right to the next to me, Federico IAgrE. Respect what is a mixing, he's a chemical engineer, I'm a food engineer. The guy to next to us is a mechanical engineer, then on the very left is an aerospace engineer. So it's an engineering gang. Two of those went down the dark route, going for MBAs, and we just stayed on the technical side. But overall, we are a very good mix. And this is the core team as it currently stands. What we have done to date, or some key achievements, just very simple. We started with a UK patent application. We got into a Innovate UK funded program called IAgrE. We basically got money to travel around, talk to companies, and some of which, such as housing sprayers, for example, which IAgrE kindly gave to the context and members were quite happy. We got some funding to develop the technology, 25K MIPIMS funding, and we created Rheality Limited later then. We did the first pilot test at a leading personal care and hair care manufacturer in Port Sunlight. We got some funding in just a few days ago. We got another few fundings in. We have a second pilot plant starting in 2 weeks' time roughly, and we are looking to two more pilots. One of them would be a Scandinavian fertilizer and civil explosive manufacturer. We're looking at the partner installation next year, the installation of factories in other markets, but just very short where we are, what we have done. So the science behind it, the technology makes use of something called acoustic emission. Maybe some of you might have heard or might have even applied acoustic emission to some extent. What it is, acoustic emissions are transient elastic waves within a material which is caused by the rapid or steady release of localized stress energy. So we have something, there's a stimulus, and that stimulus leads to the release of such energies. It's an irreversible release of energy, and these acoustic waves will always travel to the surface. As said, you might have had it yourself, maybe one of your application fields or workplaces is very, very traditionally used to look at material fatigue or material failure, welding application, but also things like friction, cavitation, impact actually give you those acoustic emissions. For the case of fluid flow, we know what drives that event, the formation of eddies and shear boundary effects along the boundary layer. On the right side, I put like a very simple schematic. Where are these acoustic emissions actually located? They are past our audible spectrum, what we can hear, and then intermeshing at some point with ultrasound. So it's not a very pure dissimulation, but just to give an idea, it's past what we can hear. There are in principle two technical executions. One is called active acoustics, the other one is called passive acoustics. Active acoustic emission is a transducer receiver system. I put a schematic up to the right side. It's not the newest of technology, it became popular since the 1980s. It's still in use. It's most popular as an execution called UDV or UDV delta P, where they have ultrasound Doppler velocimetry measurement paired with differential pressure measurements. The advantages of using such an active system is it's a proven technology that is very well understood in fluid manufacturing. A lot of application, and maybe many of you might use that, is for leak detection for very moderate distances. However, since we have the transducing system, we have a constant need to have an energy input. So it's high in energy consumption, it builds up. It is very limited to multi-phase flow. So if I have gas or solids present in my flow, in particular when I move to large diameter pipes, they would be present in oil and gas applications. So as you know, certain fertilizer manufacturing and civil explosive applications. For industrial solutions, they are very expensive. For full-scale one, they start at £100,000, £150,000, with all the hygiene certification and everything in the food environment. What we use is a passive system. A passive system is, it looks simpler. It's a receiver system only. We have one sensor listening to the process, and it only detects the energy the process or the material will release by itself. So it's very traditionally applied, as I said, to material heat measurements, often applied to bridges or railway tracks to look at corrosion over time, but also to techniques. In chemical engineering, in some countries actually recommended standard is to use acoustic emission measurements and passive acoustics to look at pressure vessel monitoring along the wall. There is a system called distributed acoustic sensing system where I just spread them around a space, and then I can have basically a dimensional feature space in 3 dimensions where my lead would be and where I can locate it. It's very popular. The advantages is it's much more affordable than an active system, less than a half in cost actually. There are no restrictions in pipe size, pipe diameter, pipe shape, whether you have a bend or not, it doesn't really matter. There is no need to add additional energy because we have a receiver system only, so the fluid passes by and then it converts mechanical energy into a current. It has a long history in construction engineering. It's very cheap and very easy to scale up. If you wanted to go for a distributed system, you just buy 2, 3, 4 sensors placing around in that particular space. However, these signals are very, very complex, and noise with signals, and this is basically where Rheology kicks in, where we make use of these hundreds of thousands and millions of data points and simplify them. And for fluid flow, that's why this PhD was originally created, and nowadays Rheology Limited, it's an entirely new technology applied to fluid flow and rheology. The technology itself, I would have loved to show a very nice picture on the pilots, on our pilot scaling rig, but lockdown came, and luckily I took the hardware with me. I haven't been able to go onto campus really properly ever since, but you see the hardware components, and they will do it for now. We have what is called the Rheology system, a mechanical piece of pipe. Normally there would be housing around it, and this would be all in an integrated unit. And we have a piezoelectric sensing unit. This is the sensor on the top. What happens is the fluid goes in and the fluid exits, so the sensor itself will not be in touch with the fluid, and we have this sort of pinhead where we have a T-shaped intrusion with the radial depth of the pipe. As said, it works for any pipe diameter. We have tried that, and what we use is, we haven't invented that sensor. It's a off-the-shelf sensor used for a different application, admittedly, but we retrain that sensor to recognize certain rheological phenomena or to correlate it to certain rheological properties. We have designed it to a plug-and-play system, so it doesn't matter what sort of flunging you have. The pipe itself is more than less the only thing that is important, and you can flunge it to whatever you want, or what diameter you want. Acoustic emissions is a non-destructive testing technique, which is quite popular and more increasingly in food and chemical engineering applications. It's a very low CapEx and OpEx requirement. I said it's much cheaper than an active solution. Then we have these like magical buzzwords I'm not a fan of, but it makes use of big data, Industry 4.0, Internet of Things trends. So I can process a lot of data constantly that flows in and flows out. It is an emerging niche segment for inline and online rheology at £450 million with a year-on-year growth of 6.5%. So it's a fairly strong growing market. And what happens is that the fluid enters the pipe segment. There is a T-shaped intrusion of a specific mechanical design. What happens is we perturbate the flow in a very controlled manner when it passes that pin, and we force the fluid then to release transient energy, and that energy would basically be conveyed through the pin to the sensor sensitive area, and then we would process it with our detection equipment. We have done some competitor analysis without naming the competitors, but they are the very standard offline rheometer manufacturers we probably all have in our labs if rheology is important to us. There are very few in situ technologies where I have a inline measurement for full industrial scale. One is a seeded system, the other one is it's not even a purchasable solution yet, but it will come to market, we know that. And what you can see is with our technology, we could do flow metering, we can do leak detection, blockage detection. It is very accurate, and we'll talk about that in a minute. We can handle any type of fluid. It doesn't matter whether it's single phase or multi-phase flow. And the algorithm we created has been designed to self-calibrate. So what we came up with, as said, we deal with millions of data points coming in. We created something called the Rheology vector. And what we hide behind that is, it is a simple sequence of parameters that can be tuned. We normally set it for 10, but that number can increase or decrease depending on whatever you want or how marginal the differences you're after. It is a sequence of parameters that will uniquely identify the rheological fingerprint of your formulation in time within seconds. Indeed, the fastest we can do is half a second. So the idea behind that rheological factor is a little bit like a DNA sequencing where we have these different acids and nucleic acids and how they then relate to each other. So we took that idea, we thought, okay, we create our own fingerprint for fluid. And what we're doing is basically we take our fluid and then we do a rheological sequencing of our formulation. So it's a very different approach from the traditional share stress, share weight relationship. It's just taking a on-the-spot acoustic measurement, and then we process the data and come up with these rheological factors. As I said, it can start with 10, but it can be 20 or 100, depending on whatever is needed. But 10 is fairly easy, but you know when dealing with some customers to capture. So current and future developments. Last year we presented at the annual conference in America from the American Institute of Chemical Engineers. We had a poster presentation. We tested complex fluids falling into a Hershey-Bikley relationship in power law fluids such as soaps, for example, and determining fluid formulations. And what is that the revolution, while we are very fine, is we actually track formulation changes of 0.05% weight percentage difference. And we could potentially go lower, but that's the lowest we can do in Birmingham with our testing so far. As said, we did different fluids. So I said power law fluids. CMC is a very standard thickener in the food industry. Then a Hershey-Bikley model is where we have carbon put, a very standard ingredient for hair care products or hair gels, and then Newtonian cases, simple cases of water and glycerin. And these would be the corresponding unique acoustic rheological factor fingerprints as we would create them across all these different fluids. To give you an example how bad the problem is or how large scale the problem is, because we did a lot of work with a hair care manufacturer called Sunlight. We were looking at the evolution of rheology for complex formulations for the hair care products. And this particular manufacturer, they produce worldwide 167 million bottles amongst their 40 production lines, just shampoo and conditioner. These two products only. They obviously have many more products. Around 20% go into waste, which would equate around about 33 million bottles per year. And the estimate is around about 40% being a fully liquid formulation, so down to rheology in this case, because liquid formulation is much easier, would be due to poor process control or lack of in situ measurement availability. So that would be 13.2 million bottles of shampoo and conditioner. At the retail value would be around about 40 million pound potential loss or actual loss per year they have, just in lost sales. Taken away the need also for disposal of all these chemicals, because the shampoo is nothing else than a chemical mixture. So we did those trials. The outcomes of the trials were at the CD manufacturer. They took 3 days time. We did 2 key categories. I said one is the largest by volume, the other one is the largest by value, because fragrances and certain effects are quite expensive to bring in. And the highlights, we achieved a visualization by the means of acoustic data and rheology evolution. We actually saw something looking at the domain of the rheological factors, that there are certain patterns appearing which might be very exciting for product development, because you could predict what is happening in the next stage, or you could say, now is the time to move on to stage 2, rather than currently how it's done, they over-process a lot, which is a lot of energy and time loss in manufacturing capability losses. What happened as well is, and that wasn't our original intention, we obviously took a comparison between our measurement and the traditional offline rheometer, and we knew there were certain ingredients going in by the law of nature. An ingredient would alter, those ingredients used would alter the rheology, but a standard offline rheometer was not able to detect rheological changes at those small addition levels, but our technology gave a very, very distinctively different acoustic response to these fluids. That's why we say we are confident to go way below the 0.05% weight percentage changes in ingredient addition, which would be very nice. I don't know if any rheologist or physicist is with us, but there is a very old dispute for more than 30 years now whether there is a yield stress or not with fluids. We might be able to get closer to an answer, getting better and better in our detection accuracy, maybe to support the claims by Barnes there isn't a yield stress. So some of the outcomes, this is actually the manufacture of shampoo. Shampoo is manufactured in 14 different production stages overall, and these would be the average acoustic fingerprints of all of these stages. And the idea would be, back in that project, rather than having the current manufacturing status based on a piece of paper and the operator feeling, we can take these fingerprints as the basis, and we know when they start manufacturing, when they hit a certain landmark, now they can move into the next production stage rather than over-processing what they do currently wrong. We can also look at a very, very short time scale. Measurement time scale is half a second, and just looking at one stage, we could see how the product is actually changing during the mixing stage, just the very same product in the same process. And if we would continue this, we could then identify the point of steady state, so they could move on to the next process stage. And the other thing is detection of leaks and blockages. We did something, and IAgrE has a very lovely journal. Because Steve was my CEng mentor, obviously, and it's a good journal. We look at different obstructions, so we can use that as an online tool to predict blockages in pipes. We can use a single sensor in fully turbulent single phase flow that outperform our manometer. I will show that in a second. And a combination of supervised machine learning and passive acoustics work very well in our simplification algorithms, and we have very high correct accuracies in prediction of 95% or more. In particular, the interesting thing of pressure drop measurements is what we see here in this singular point, the green circle one, these like two, the pink one and the green one. The difference is 0.001 bar in that measurement. It's very, very marginal. At some points, we actually got also where the manometer wouldn't even say there's any difference in pressure drop across different geometric obstructions, but we actually get different acoustic responses. This would be the very raw signal in its frequency domain, but when we then simplify to those fingerprints, we see a much, much stronger difference. So we can actually distinguish where traditional methods would fail to do so. So we started doing some work that's more a passion of mine, cleaning and biofil formulation. Maybe because I'm German, we like things cleaning, but I don't know. I always had a passion for pipe cleaning, so we started to look at pipe cleaning. We would be happy to provide service an industrial partner. We know cleaning is a big problem from everyone having a heat exchanger in place, but we wanted to do some more validation work with a visual method called CLIF, canal laser induced fluorescence. because what we did is, back then when we did the first trial campaign, we did independent trials beforehand on fouling. We took them just as a very quick clean down, we did a cleanup of the line and took measurements as well. And we were actually able to detect overall pipe surface consumption, so basically leftover dirt after cleaning of as little as 5% in this particular study, or when we did the cleaning down of our conditioner line. There has been a little bit more stuff been published from biosystems engineering. Two of them are in German, so probably not really applicable. One has been on food. Another one is actually coming up on multi-phase flow. It's currently, we just do the final editing bits, International Journal of Multi-Phase Flow, and we are currently also working on one on these different care products. To give you a very short summary, rheology matters, I believe, for everyone. Maybe you're not aware, but it does matter. It is very challenging to assess rheology in situ and in real time. There are very limited and few applications available. Rheology offers a simple solution that can monitor rheological changes for your process in time, and it is non-destructive, so it's quite attractive. It's a very hygienic solution if you would look into food and pharmaceutical applications, because obviously the sensors never touch with the fluid, so wear is a very marginal point as well. We are capable to monitor very, very small changes in the system, which I have shown today as some examples. We always look to some industrial partners and interesting projects being born of academia. And well, if you feel free and you're interested, we have an advisory board. We're still looking at some people. So if somebody has me someone in mind, feel free to get in touch with it. And I'm going to close with a very cheesy slogan of ours: we are here to listen to your process. So thank you very much. And I hand over to Sarah for the questions and answers.
Thank you, Daniel. That was absolutely fascinating. I've scribbled a page of notes here about things like acoustic fingerprints, which is a way of me making it sound like I understand what I'm talking about. And I'm sure it's much more complicated than that. This is now the opportunity for questions. So does anybody have any questions? You will need to, Sarah, has everybody's microphone been unmuted? First question.
I think they can do that themselves now.
Yes, right. So if anyone has a question, either put it in the chat.
Daniel, could you stop sharing screen, please?
I could do, unless somebody wants to jump to any particular slide.
Okay.
Yeah, I mean, just ask the questions and I will answer.
Right, fire away.
That was most interesting. If I could just ask, presumably then, if you want to use this process for monitoring where things are going wrong, in a way, if you are recording the acoustics of a machine that's working right, when it deviates from that, you can then see that there's a problem, apart from, you know, losses and other ways of doing it. But so perhaps using sound in this way could give you a sort of an early heads up.
Yeah, I agree. The original idea, the very original idea, was actually to look at something where we can have a process monitoring tool in place. And having worked in food, we waste a lot, and you would be shocked how much food we waste. Not just taking what we put into a skip, but also what we then somehow mix up with other stuff to make bad stuff look maybe only half as bad. Or when we go to 1 pound shops, so there's the reason why these things are sold for £1 and not for their true value, because they aren't maybe that great. But yeah, so as I said, the self-calibrating bit plays into that question and suggestion. What we normally do is when we set up the equipment, we would say, we start running a process, and whenever you are happy with the process, that would be basically our landmark recording, and we would always compare against that.
I have a question from Declan, which he's put in the chat box here. I don't know if you can see that, Daniel, but as well as the sensor, did you say there's another item inside the pipe?
Yeah, so let me go to the slides. Maybe I should put them open. So yeah, there is another part in the slide in the pipe. So I said this would be the part where the sensor is sitting on it, and basically throughout this one, the depth of the radius would be the best resolution. You can have it shorter or longer. This is just a standard execution. Basically, the radius would give you 100% resolution. But for example, for the Scandinavian customer, they want to have a very short and thick pin bit. But yeah, there is a protrusion into there, a little pin where the fluid would pass by, which is necessary purely to convey the signals or the energy releases between the fluid and the sensor.
Rashid has asked a question here as well. How is big data utilized in your process?
Okay. So normally when we set it up, it depends for the application. Some applications, we know, for example, conditioner is a very lengthy process that will only take a measurement every 5 minutes. Some of them, we know, they take every 3 minutes a measurement. It depends on your process and your understanding how important it is to have product data. But as I said, we would take in all this data, it would go into machine learning, and what we currently work on is, and that's maybe a challenging one, is to have a sort of cloud solution in place where we would then have already a library of things where then over time the process would optimize. We're getting a software engineer because the key challenges around that is no manufacturer is happy to give away their manufacturing data, obviously, to third party, which is a challenge, but there are ways around to anonymize it. And obviously there are things like Amazon AI or Google AI, which do nothing else than that. But as I said, we get the software engineer and you have this big data cloud solution idea implemented.
Okay. Anyone else got a question?
Yeah, Andy.
Richard.
Yeah, we make piling rigs, and we have to monitor concrete being pumped down the inside of an auger as it's pulled out of the ground to create a pile. Can you monitor something with so much aggregate in it?
Yeah, so as I said, for us, it sounds strange in a way, right? It's not strange when you have the physics behind it. For active acoustic emission systems, it's bad if you have, let's say, cement grouts or you have solids present or bubbles, purely because they send the signal out. If you have bubbles or solids present, either the signal would deflect or it would just be swallowed up. With a passive system, we are happy for anything else than just the fluid phase in there, because it actually enhances the signal. So for us, if you want to pump concrete through, and it must have a certain rheological key or a certain key rheology, it's much better for us to deal with those materials and with pure liquids passing through.
Okay, so I mean, we have to monitor that to show that the system has worked. At the moment, there's crudely is a flow meter and pressure measurement, and they suffer really badly because they're not happy with the obviously wear, and then the concrete sets around them, and you have to throw them away and put new ones on, which is good for the spare parts trade. But
yeah, I mean, there's one big issue. I mean, there are two big issues with flow meter. I guess you probably would go for a traditional one, which is the electromagnetic one, where you're only calibrated on water. So the number it gives you is anything but not what is truly passing through your pipe. Which is a known problem because they're just water calibrated, and that's the way how they work. You could have a Coriolis flow meter, much more expensive, but I wouldn't recommend to put down something very abrasive like a cement fluid, purely because you wouldn't have a lot of joy with it for a long time. The one thing is, and me being a food engineer, we have something called vari vent housing. I don't know if you know that. It's like a plant you put in. So rather than having a permanent installation like on the picture, which is our laboratory prototype scale, is something where you could remove that pin. You have just a blank you put in, and then you can flush through your system. But that's currently the design phase. Because we acknowledge the problem, it's not great for some things to have the intrusion in there, but we need it in order to get the signal. But as said, I mean, we are working on this application, so you would basically just take out the piece with a pin, take it out, you can wash it down externally, and then you have blank, and then you just normally just flush it through or whatever your standard procedure would be for cleaning down.
Yeah, I mean, it does, obviously, all the rest of the system gets washed out anyway. So.
Yeah.
But
also the other thing is a piece of metal, a metal rod. Okay, it has a certain design, but even if that metal rod, stainless steel isn't that expensive to replace than having a flow meter to replace. I can promise you that.
Oh, thank you.
So, another question. Someone give me a question, or I'll have to start asking up. Paul's put his hand up.
Yeah, Daniel, it's possibly not directly related to the technology, but you mentioned you were doing some work at Port Sunlight.
Yeah.
Production. And you quoted numbers of 30% wastage in the process.
Yeah.
I mean, to me, you know, they've been manufacturing pharmaceutical chemicals at Port Sunlight for very, very many years. And I'm staggered that today, you know, they have that sort of issue with the process. What sort of physical issues would you be able to help identify that would cause that level of wastage in their process?
Yeah, I mean, the true number of waste would be higher, but I wouldn't say these numbers are particularly bad. If I would tell you how many Weetabix go into pig feed rather than onto the shelf in your supermarket, you would be shocked. I mean, there's a reason why there are hardly any feed manufacturers left in Northamptonshire, because those pigs live happily in Weetabix. It is sad reality, and I feel a little bit sorry for the farmers growing such a lovely wheat and then it ends up there. But the true issue is much higher, because as I said, the one thing is they do, because it's a worry they now and they're well aware of, they tend to over process. So they mix longer, they heat longer, so the waste of energy is even higher. So we don't even take that into account.
Right.
As said, the problem is with a traditional rheometer, what would happen is they go down the factory line, they would take a sample, they would go to the lab, but a traditional rheometer measurement takes around 30 to 60 minutes. It's a long time process, but in my factory, we have a constant stream of product passing by. In that case, they have a semi-batch process, so it's like a continuous stream made from batches. So by the time they know there's a problem, they have already produced an hour worth of product going into waste. That's how they end up with these big figures. So hence the need to have an inline solution. And there are not many out there. And with that particular one, those active acoustic emission things, they tested it. That didn't work. The pipe diameter is the main restriction. And then for many of those personal care products, where air is a very cheap ingredient and it gives you like some sparkly bubbles in there, for example, they do gassing in their product. So you have like a bubbly product you see then in your body. You know, sometimes you have these like shiny things that just tiny air bubbles in there, nothing else. And those systems wouldn't work then. Or there are other things like laser systems, which obviously have problem with health and safety. You wouldn't want to have a high intensity laser firing in a manufacturing line. Taking away the cost of $500,000 for these PIV systems, but yeah, so that is why we try to come up with a solution. But the waste figures are pretty much standard. I mean, I have seen worse in my professional career in food, certainly worse. I don't know how it is in agriculture engineering. I said I'm not an agriculture engineer, but if you might add up everything, you might eventually also end up there.
Okay, thanks.
I was starting to think about more traditional agricultural liquids, which may or may not have consistency problems. And you know, I was starting to scribble notes about slurry and also whether rheology has anything to do with identifying nutrient constituents and things like that, which may be completely off beam. But I just wondered what thoughts you had about application outside of the food industry, really, Daniel.
Yeah. So as said, we are just about. I mean, COVID kicked into everything. We were about to do a project with a Scandinavian company, And they do two main products. One is fertilizer and one is civil explosives. Don't ask me why that combination of products, but I guess, I mean, you can easily make explosive from fertilizer. And they have a particular problem with crystallizing. So apparently when you produce fertilizers, you have a crystallization phase. And to understand, to have a very consistent product, those crystals need to go in a certain way. And they currently can't assess it. What they use is a Brookfield method. It's a viscometer. The problem with a viscometer is they are inaccurate. Plus minus 10% is what literature says. It's the most popular technique still to date. But that's what they use in agriculture mainly, apparently. I think the other thing is spray applications, because if you spray stuff on your field, as the gentleman said before, I think Richard said, you have a flow meter. I would bet in agriculture applications, they are all either electromagnetic flow meters, most likely maybe some Coriolis. So the number they get on their reading, what they spray on the field, doesn't necessarily mean that's the true number they spray on their field. And I can imagine some of those crop protection sprays you put on are not particularly cheap. So to have a way to have a very well-defined flow measurement would be very good, I think, for agricultural practice. The other thing is, I know because IAgrE also has an environmentalist side, sludge water treatment. If I have, well, sludges I need to deal with and process, then we have a project, not my project, but they look into water purification and desalination. So actually to use acoustics to find the point where I actually have clean water, because that original idea was actually born from a NASA project, because what happens in space is our shot. What happens in space is in NASA, I've learned two things from NASA, which was quite shocking. The one thing is NASA wants on Windows 98 still, which I wouldn't have thought still exists, but it does at NASA. The other thing is when they send the people up to space, they reclaim the urine and form that back into water. So they basically drink their own urine, cleared down.
Marvelous.
But they have no tool to date, NASA being NASA, and we have all this picture of amazing NASA, or I had it at least, being a high-tech company. What they still to date use is some density tables from the 1940s, 1950s, to find the point when I have water and not urine. However, they know these density tables are particularly in space because the physics changed at some point, obviously. And it's not the most accurate measurement when they do it with the current equipment, because they can't take a lot of fancy equipment up there. You never really have quite water. I mean, just to make it this way. So the hope was, since rheology of water is very well known, take the fingerprinting idea and keep your recirculation process running as long as you're confident you have clean water you give to your astronauts up there, then giving water plus X to your astronauts. And I think the very same could apply to reclaiming wastewater and sludges in agricultural practice.
So just in case you were harboring an ambition to go and become an astronaut, you know, that may have just put you off the thought. I guess that's the price you have to pay for going to space and all, and your future career of book writing and all the rest of it. But that is fascinating, Daniel, that NASA have no accurate way of working out when it's no longer we before you drink it, other than presumably sort of swirling it around in the glass and giving it a sniff.
It is sadly true. I mean, the reason behind it is, as I said, they can't take up there a lot of fancy equipment. They can't physically because it's very expensive. It's very limited space. But relying on, I mean, okay, I know I'm working engineer and we rely on very old tables sometimes. I mean, these moisture tables or whatsoever, density tables and heat transfer tables are sometimes from very 1930s and probably not very accurate if you would compare it with accurate measurements nowadays. But they take some stuff up and they physically can't. So the idea is if I have a tiny sensor and a piece of pipe, I can have even a spare with it. It's much more attractive to take up there than relying on the density tables. But hey ho, what they do on the ISS for now is drinking water-ish water.
Do you have, Daniel, an indication about what one of your systems would cost, or a typical idea or a model of how you would commercialize it?
Well, I mean, we have a CEO for that. as said, I would say I'm a dumb engineer. I'm a food engineer. I'm one of these grease monkey engineers which like to go into a factory and build stuff or fix stuff. I'm not like one of these engineers sitting down on a piece of paper and filling in gunshots all day. I'm one of the talented engineers that actually do this stuff. So I don't have a costing particular for that because I know he does it based on the cases. I mean, purely some things are just put it down. 4-inch piece of pipe costs obviously more than a 1-inch piece of pipe.
Yeah.
Then some people want to have 2 sensing units, and then if you buy at certain points, it's getting cheaper, or how you want to configure it, or whether you want to measure only every 10 minutes, or every 20 minutes, or every second. But as said, if anyone has questions to that, I mean, obviously Sarah has my contact details. I'm sure she can happily share that out, and then I'll just link it to Andrea, our CEO, who can give you then for your particular application a costing.
You have a great career in politics ahead of you, Daniel, with that answer. That's all I can say. I'm glad you asked me that question, Andy. Is what you can say. Does anybody else have any questions? As the auctioneer says, going once, going twice, going 3 times, or speak now or forever hold your peace. He says, jumping analogies quickly. Daniel, on behalf of myself and the institution, and certainly everyone who's taken part today, thank you very much for a fascinating insight into your world.
Yeah.
I really appreciate it. You've given me some thoughts for a future piece in Landwards as well, so I may come back to you on this in due course. I understand the presentation will go out on the IAgrE Landward on the website rather than Landward. Sorry, mixing my metaphors. In due course. So yeah. Thanks, Daniel. It's been great. It's been an insight into a world which you know, old fuddy-duddies like myself don't necessarily think of very much in our ag engineering journey, and yet, you know, vitally important and with some great applications. So thank you very much for that.
Well, I have to say thank you, and as said, if anyone has any other questions, feel free to drop me a line, or where I said the presentation will be shared out there, all our contact details. Thank you, Sarah, for monitoring everything and setting up.